Hello all, welcome to this video on distributed computing. Today I'll be talking about Suzuki Kasami's broadcast algorithm. The Suzuki Kasami broadcast algorithm is a token-based algorithm for mutual exclusion in distributed systems that was published in 1985. Ichiro Suzuki is currently a professor of computer science at the University of Wisconsin, Milwaukee. His research interests include distributed systems, concurrent systems, computational geometry, and computational robotics. Tadao Kasami was a noted Japanese information theorist who had significant contributions to error correcting codes. Now, this algorithm is a modification of Riccata-Agrawala algorithm, which uses request and reply messages to gain access to the critical section. The Suzuki Kasami algorithm adds a privilege message, which we call here as a token, that allows a node to hand over the critical section to another node. Now, this is an overview of the entire algorithm. If a process wants to enter the critical section and if it doesn't have a token, it broadcasts a message, which is a request, to all the processes in the system. The processes that has the token will then send it to the requesting process. However, if that process is in the critical section, it gets to finish before sending the token. A process holding the token can continuously enter the critical section until the token is requested. Now, this is a request vector for process I. So, the request vector will contain the largest sequence number received from a process K in its request message. Similarly, there is a token. The token will have a vector and a queue associated with it. So this vector will contain the sequence number of latest executed request from a process K, and Q is the set of requesting processes. Now we'll see the algorithm in detail. So the first section is requesting the critical section. Now when a process I wants to enter the critical section and suppose it doesn't have a token, what it does is it will increment its sequence number in the request vector. Suppose the initial entry was 0, it will be incremented, so the value is 1. Now this request message containing the new sequence number is sent to all other processes in the system. When a process K will receive this request message, so the request message will contain the process ID and the sequence number. So it will set its corresponding request vector value for that corresponding process I to the maximum value of the sequence number or its current entry in the request vector, which we'll see in detail in an example after this. Now, if the sequence number received is less than the entry in the request vector, then the message is outdated. Now, if a process K has a token and it's currently not in the critical section, and it checks for this condition, if the entry in the request vector is equal to the entry in the token array plus 1, then it will send a token to that process. That is all with the requesting critical section part. Now there is the executing critical section where the process enters the critical section when it has acquired the token. After that, it releases the critical section. So there, when a process I leaves, it will set the value in the token array to be equal to the value in the request vector of the process I. Now that will indicate that the entry in the request vector will tell us that that particular request was executed. Now for every process K whose ID is not there in the token queue, what it does is it appends its ID to the queue if this condition is satisfied. That is, the request vector entry is equal to the token array entry plus 1. So that will indicate that the process K has some outstanding requests. Now if the token queue or the token array is non-empty, it will delete the ID of the process from the head of the queue and sends it a token. So that way we give priority to the request of other processes also. Now if the queue is empty, the process will keep the token to itself. Now looking into the correctness of this algorithm, mutual exclusion is guaranteed because there is only one token in the system and a site holds the token during the critical section execution. Now the theorem states that a requesting site enters the critical section in finite time. Now looking into the proof, the token request messages of a site SI will reach other sites in finite time. Now since one of these sites will have a token in finite time, site SI's request will be placed in the token queue in finite time. Since there can be at most n-1 requests in front of this request in the token queue, site SI will get the token and execute the critical section in finite time. Now looking into the message complexity, the algorithm requires zero message invocation if the site already holds the idle token at the time of critical section request, or maximum of n message per critical section execution. This n messages involve n-1 request messages and 1 reply message. A drawback of this algorithm is that a site will retain the token even if it doesn't have requested for the critical section. Now the performance of the algorithm, the synchronization delay is 0 and no message is needed if the site holds the idle token at the time of its request. In case the site doesn't hold the idle token, the maximum synchronization delay is equal to maximum message transmission time and a maximum of n messages required per critical section invocation. Now we'll see an example of this algorithm in detail. So here we have 5 processes 1, 2, 3, 4 and 5. Each of them has a request vector which will contain an entry for each of the process in the system. So this is the request vector for process 1. The entry here is 5 because the total number of processes is 5. Initially all of them are set as 0. So we have a token. A token will have a token queue or array along with a queue for maintaining the pending request. Now these both will be updated by the node that holds the token. So this array will contain the sequence number of requests granted most recently by the node and the queue will contain the requesting nodes. So for the request to be granted, the entry in the request vector should be less than the sequence number received in the request. Any request not satisfying this will be an outdated request. So Sn will be the sequence number which will indicate that the node is requesting for the Sn plus 1th critical section invocation. Now node 1 is sending a request message. So it will update its entry in the request vector by 1, incrementing it. So initially it was 0, now it is 1. The request will contain its ID and the sequence number, which is 1, 1. Now, after all the processes receive the request, they are checking if the request is outdated or not. For that, they check for this condition if the entry in the corresponding request vector is less than the sequence number. So, after checking it, we'll see that it's 0 less than 1, 0 less than 1, again 0 less than 1, 0 less than 1. So, everywhere it is true. So, all the nodes approve the request. So what happens is they will all update the corresponding request vector value for process 1 as 1. Now let us assume that node 5 has the token with it. So the token will have a token array and a queue. So after it got the request from node 1, it will place it in the queue. And when the node 5 has exited the critical section, it will send token to process 1, update the queue, that is removing its entry from the queue. Now 1 has got the token, so it can enter the critical section and the queue will be empty. And what happens is the token array will be updated as token array value will be equal to the request vector value of 1 in 1, that is 1. So the value here will be 1. Now suppose we see that after a few of these interactions happen, we take a case where the status of the request vector array of all the nodes have these values, and now suppose node 2 has the token and it is currently executing in the critical section. We see that in this diagram, node 5 is sending a request. So 5 has its ID and its sequence number value. So the 7 plus 1, that 8, will be sent to all the nodes. Now 5 has requested for the critical section. Token is granted only when 2 has completed the execution of the critical section. Now all the processes will check if this request is valid or not. For that, they'll check the corresponding request vector value along with the sequence number received. So for 1, it is 7 less than 8, 7 less than 8, 7 less than 8, and 7 less than 8. So all the nodes are approving the request. Now after that, all the nodes will update their corresponding value as 8. Now node 2 is still executing in the critical section. Now suppose node 1 has requested for the token. So token will be available only after 2 has completed its execution. So the request from 1 will be 1 comma 6. So earlier it was 5, 5 plus 1, 6. So that is sent to all the nodes. Then all the other processes will check if this request is outdated or not. For that, this condition is checked. So the corresponding entries for process 1 will be checked in. So here you can see that 5 is less than 6, 5 less than 6, 5 less than 6 and 5 less than 6. So all the nodes will approve the request. And they will also update the corresponding request vector value as 6. Again, node 2 is still in the critical section. Now node 3 is requesting for the critical section. So it sends the message which contains its ID 3 along with its sequence number updated. So it was 4 here. 4 plus 1, 5 is sent to all the nodes. Now other processes are checking if this request is outdated or not. So for node 3, 4 less than 5, 4 less than 5, 4 less than 5 and 4 less than 5. So all the nodes will approve the request. And they will update their corresponding entry for 3 as 5 in the request vector. Now you can see that it has time for completing the critical section execution for node 2. Now according to the algorithm we discussed before, it checks for this condition. If the request vector values for all the processes in process 2 is equal to its corresponding token array value plus 1 or not. Now when this condition is checked, what happens is, even if the process has not requested for anything, even if it's not available in the queue or not, if this condition is satisfied, it will be placed in the queue. So what 2 does is, it will go and check the condition and it will start removing each of the processes from the top of the queue and one by one and send them the token. So the condition is checked here for this. These are the entries of the request vector for process 2. R21 is 6. Token array entry is 5. 5 plus 1 is 6. So 1 will be placed in the queue. for the process 3. 4 is the entry here, 5. 5 is equal to 4 plus 1. So 3 will also be placed in the queue. Next is 4. This is 2. 2 plus 1, no, they are not equal. So process for request is not placed in the queue. Next is 5. It is 8 here. So we have 7 plus 1 is equal to 8. So it is satisfied. So 5 will be placed in the queue. Therefore, these three are the outstanding requests here. Accordingly, node 2 will update its queue and token array. Now it will update the token array value for 2 as 3. 2 will check if the queue is empty or not and remove one node from the top and send it the token. So here it is 1. Now 1 will get the token from node 2 and it can enter the critical section. So we can see that in the example, in the drawing I explained before, the request by the nodes was in the order 5, 1 and 3. But that is not the order that I explained here. We placed this as 1, 3 and 5. So that is because the requests that were sent doesn't have a timestamp. So what node 2 does is it will check for the outstanding request in the order of array elements. So it will start from process 1 to process 5. So if you take that order, this 5, 1, 3 will become 1, 3 and 5. So even if you are considering the order as 5, 1, 3, there will not be any kind of starvation happening. So take this scenario, current scenario as this. This was the last updated value for the queue 3, 5. Suppose process 1 has requested for the critical section. Now this request by 1 will be placed only after 3 and 5. So again there will be no starvation with this mechanism happening. Now after critical section execution, node 1 will update its token array. And what happens is, as node 3 is on top of the queue, that will be removed and token will be sent to 3. And later 5 is there. After 3 has completed the critical section execution, token will be sent to 5 and it will be removed from the queue. Now the ln value will be updated as the 7 being converted to 8 and 4 being converted to 5. Now we'll look into the case of an outdated request. Now suppose node 1 gets an outdated request from node 5, which is 5, 6, which was sent a long time ago. Token is with 3. Now it checks the condition. If its Rn value for 5 is less than the sequence number. No, it is greater than the sequence number. So the condition is violated. So based on that, node 1 will discard the request by 5. Next is the outstanding request. Suppose 3 has the token. 3 is in the critical section. And suppose 4 is giving a request along with its request vector value being 3, the sequence number value. And it is sent to all the other processes. 3 is still executing in the critical section. Now all the processes will check if this request is outstanding or outdated. So to check if it's outdated, this condition should be satisfied. So for 2 is less than 3 here, then again 2 less than 3, 2 less than 3 and 2 less than 3. So all the nodes will approve the request here. Now 3 is still there in the critical section, and node 4 is requesting for the token. So the corresponding request vector value for all the processes, the entry at 4 will be 3. Now after exiting the critical section, 3 will check for its outstanding request. That is, this condition, the request vector value is equal to the token array value plus 1. So in this example, node 4 is an outstanding request. As usual, it will check all the process values whether anybody else needs to be in the queue or not. So you can see that all of them will have the same value here. So we'll check for all the processes 1, 2, 3 and 5. All of them have the value 3. So this 3 is the same value as the value in ln plus 1. So what happens is 4 will be placed in the queue. After exiting the critical section, node 3 will take the request from the queue, remove it and give the token to node 4. Now 4 will execute in the critical section. After execution in the critical section, the value, its token array value will be updated. So initially the value was 1 less than that. So after exiting the critical section, the value is updated. That is, the ln value of 4 will be equal to the request vector value of 4 in the fourth place. That's all for now. Thank you for watching.